The second method is a little more involved, a little more complicated than transit, but it's worth it, and you'll see why. Has some good concepts in there too, so definitely a good thing to know about. The second extrasolar planet detection method we have is called the radial velocity method. So, I'm going to draw another diagram of a star with a planet orbiting it. Now, if you recall the Kepler-Newton assignment, you may recall a problem regarding Sirius A and B, two stars that orbited each other in a binary pair, and they both orbited the center of mass between them, because they were so close in mass that instead of one orbiting the other, they both orbited a point between them. And we think of that as being kind of different from, like, the Earth orbiting the Sun. We tend to think of the Sun as standing still and the Earth going in circles around it. But that actually is not the case. The Earth and the Sun are also both orbiting around the center of mass of the Earth and the Sun, just like Sirius A and Sirius B. It's just that the Sun is so much more massive than the Earth that the center of mass of the Earth and the Sun is just a little bit off of where the center of the Sun is. So, the Earth is making these big dramatic orbits, and the Sun is just making very small orbits. You know, it's just kind of, it's almost just kind of wiggling, right? But it is moving. It's definitely very appreciably making its own little orbit, while Earth makes its very large orbit. And that's important for this method. This is something that happens whenever something is orbiting something else. They're really both orbiting the center of mass. So in this case, if we have this planet, it's making this big orbit, and the star making a much smaller orbit, but it is making an orbit, right? It's moving in this circular fashion over time. Let's say the Earth is over here. Now, to explain how the radial velocity method works, you need to know about something called the Doppler effect. The Doppler effect is a concept in physics and the way waves work. Kind of the classic example of the Doppler effect that I think most people would be familiar with is you're on the road, stopped, and you hear an ambulance coming up behind you. You hear its siren, and as it's coming up on you, you hear its siren sound high-pitched, right? It almost sounds like it's getting more high-pitched as it's coming towards you. But then it comes up on you, it passes you, and as it passes you and starts driving away, the siren becomes lower pitched, as it goes away. That's an example of the Doppler effect. The Doppler effect is something that can happen to any kind of wave. In the case of the ambulance, it's happening to sound waves, but it can happen to light waves also. So here's generally how the Doppler effect works. Let's say we have a thing that emits a wave. It's a wave-emitting thing. The wave could be sound, it could be light, you know. I'm just keeping it general. Now, we're kind of used to drawing waves like this. something like that, where it's got peaks and crests, and peaks and crests, right? And you draw it all out. I'm going to, for this, draw waves in a slightly different way. I'm going to draw waves like the waves that this wave-emitting thing is giving off, like this. Where here, each line is like the crest of is like the peak of a wave, right? And then the valleys between each wave are in here. I'm not going to draw them. I'm just going to kind of leave them implied by the fact that these are all the crests. And they're about evenly spaced. This is emitting a wave of a constant wavelength, right? And then here's a person who is observing the wave and learning about the wave's wavelength. If it's sound, the person will get information about its wavelength from the pitch of the sound. If it's light, the person will be able to interpret its wavelength as the color of the light that they see. In either case, this is a person who can tell something about the wavelength by observing the wave. So this is like the normal situation. But now, let's imagine a slightly different situation. We have the same wave-emitting thing, and it's emitting the same kinds of waves in the same way. Except now, it has a speed. It's moving towards the person with some speed. So here we can kind of see that, you know, as it was emitting these, it would like emit a peak, and then a certain amount of time would pass and it would emit another peak, right? So here, it emits a peak, like normal, and then the same interval of time passes before it emits another one, because it's emitting in the same way. But now, when it emits the first peak, it's moving towards that first peak in the intervening period before it emits the second peak. So that causes the second peak to be closer to the first peak. And then it does the same thing, moves closer to the second peak before it emits the third peak, and the fourth peak, and so on. And so the result is that even though it's emitting the wave in the same way it is here, the person it's moving towards sees a wave that's been squished. It's been compressed into having a shorter wavelength. If it's a sound, he's going to hear the sound as being higher pitched. If it's color, he's going to see a color associated with a shorter wavelength because of this thing. And conversely, if the light emitting thing has a velocity away from the person, whenever it emits a peak, it moves some distance away from that peak before it emits the next peak. And it moves some distance away from that before it emits the next peak. So the person sees a wave that's been stretched out into having a longer wavelength than it normally would. And this is basically how the Doppler effect works. In the context of, like, astronomy, in the context of the Doppler effect on light specifically, if we think of this wave-emitting thing as being like a star, and it's emitting light towards us, then we actually have some special terms. If the star is moving towards us, the light we see from the star is getting shorter wavelengths. And if you recall the visible light spectrum, blue is light on the short wavelength end of the visible light spectrum. So we can sort of think of this star's light as getting bluer. And so we call this blue shift. And by the same token, this star's light is getting longer wavelength to us. And And if you recall, in the visible spectrum, red is on the long wavelength end of visible light. So we can think of this star's light as getting redder, so it's called redshift. It's called redshifting. Okay, so I think that about covers the Doppler effect. Now that you understand the Doppler effect, we can understand radial velocity. So again, we can't see this planet. It's too small, it's too dim, too far away. But we can see this star. And you can see that if this star, I'm going to make its orbit a little bit bigger. It's moving like this in a circle. Then when it's in this part of its orbit, it's moving away from the Earth. And a little bit later, when it's in this part of its orbit, it's moving towards the Earth. So we can see that because of the little orbits this star is making, that periodically the star will be redshifted for a while, and then it'll be blue shifted for a while, a little bit later. And this should happen on a routine basis. And using this, again, if we see this happening consistently over time, we can conclude there must be a planet there that's causing the star to do this. Now, this is really nice because, like, you can measure how much it redshifts and how much it blue shifts to get an idea of how fast it's going. With the period and stuff, you can get a really good idea of how massive the planet is from this. You can get all sorts of information from this. It's really great. You might be able to get that information from here too, but I think it would be harder. And it's certainly less obvious how it would work from like a math perspective. Anyway, so that's the radial velocity method. But the radial velocity method also has a problem with needing to be lined up, like the transit method. Right? If we have a solar system like this, now the star's orbit is like this. It's like the star is moving. However, the Doppler effect, you may recall, is dependent on an observer, right? It happens only when the source of the light is moving towards or away from the observer. We're the observer here on Earth, but this star is just moving up and down and side to side relative to us. It's not moving towards or away from us at all, so we won't see any redshifting from this star's orbit. Some aliens down here might, but we can't. However, so this is kind of the same problem that the transit method does, but it's not as bad for the radial velocity method, and here's why. So this orbit is just like perfectly lined up. It's lined up just right. But what if we had an orbit that was something like this? Something very much like that, actually, where it's like, it's not lined up, but it's kind of close to being lined up. Certainly closer to being lined up than this. In this case, the star's motion kind of goes in this sort of way. Now we can think of the star's motion relative to Earth as being like a diagonal line here, right? Draw it like that. But a diagonal line we can think of it as a combination of a line towards Earth and a line up and down with respect to Earth, right? So in this case, we would not see Doppler effect from the full motion of this. But we could see the Doppler effect from this part of the motion. The part of the motion that's towards and away from Earth can cause some red shifting or blue shifting. Now, it's going to be a smaller amount of red shifting and blue shifting than if the whole planet's velocity were towards or away from us like here. So it'll be harder to notice, it'll be harder to find, but we could find it. So this one, even though it's not as lined up as well as we would like, we still have a shot at finding this planet using radial velocity. Whereas in the transit method's kind of all or nothing. You're either lined up well enough or you aren't. And that's that. But with the radial velocity method, it's possible to be lined up not great, but still be able to find the planet. You'll have a harder time of it, but it's still possible. So that's why the radial velocity method is really nice. Is there anything else I need to talk about here? Okay, yeah, there's one thing. So we've found quite a few extrasolar planets using these methods. We even made a space telescope called Kepler, which was specifically designed to use these two methods to look at a certain area of the sky and the stars in it for like an extended period of time, so it could look for transits and radial velocity redshifts. Found a bunch of them. And one kind of planet we found really frequently are called hot Jupiters. They're gas giants that are like Jupiter-sized or bigger, but are really close to their stars, sometimes closer than Mercury is to our sun. Now, for reasons I've maybe discussed in a previous video, I'm not sure, we think that gas giants can't form close into stars, because for gas to kind of start to clump together and condense to start the process of forming a planet, it needs to be kind of cold. So if it's really close to a star, it can't really do that. We think that the hot Jupiters formed further out and then spiraled into a close orbit. Now this sounds like a really crazy, weird thing to happen, but we found a bunch of hot Jupiters. Like a bunch of hot Jupiters. Now there are two possible explanations for that. One, hot Jupiters are really common. Maybe. But maybe not. If you think about it, a planet that's really big and really close to its star is going to block a lot of light for the transit method, right? So it'll be easier to see, to notice a star dipping in light from a planet that's really close to it and really big, especially because the planet is also going to be doing fast orbits, so it won't take you as long as some other planets to see it happening 3 or 4 times and be able to confirm it, right? And with the radial velocity method, if the planet's really big and really close to the star, that's going to make the star's orbital motion faster, bigger, more dramatic from the stronger gravitational influence, so it's going to make the radial velocity method easier too. So it might be that hot Jupiters aren't really common, it's just that with the methods we know how to find extrasolar planets with, hot Jupiters are just really easy to find using these methods. We don't know. But, I think that about covers extrasolar planet detection.